design and select an ESP for the well and perform well simulation with ESP in place using Pipesim 2014.1. I have the base model ready for this demonstration with all the necessary data complete. Now to perform ESP design, I can simply launch this ESP design task. The left hand side of this task page displays some of the boundary conditions as well as design parameters. These are initialized from the base model. However, if you want to design for a future date during the life of ESP, for example, in this case, I'm going to change this pump depth to 8100 feet and the reservoir pressure for a future date, let's say it is 2800 psi. And imagine the gas oil ratio has increased to 200 and also water cut has gone 40% respectively. Now these are for the worst case scenario I'm going to design. Now you can see on the right hand side there is this place for plot area. As I specify outlet pressure, which in this case is at the end of the well, which is top of the riser. And you can see this initial nodal plot is generated. Note that this nodal plot is based on the nodal analysis point placed at the pump intake depth, which is 8100 feet in this case. And also this nodal plot indicates that the well is not able to produce on its own and definitely need ESP, as we are going to do in this case. You will notice that any of the parameters changed here will update this nodal plot. For example, if I change the gas oil ratio to 220, I can see the nodal plot triggering again, and let me reset it back to 200. Notice here that the pump selection option is still not available, but as we specify the remaining missing parameter, which is the target design rate, in this case let's use 5000 barrel per day. Now you can see the plot has updated, showing the target rate on the nodal plot, which gives indication of how much delta P you are going to need. And you can also see at the bottom the gas volume fraction that is going to the pump. Let's use a gas separator here and keep the separation efficiency to 47%. Now this pump selection option is active. In order to select pump, we are going to click this button, which takes to the pump database. Note here that this displayed ESPs have been filtered based on what fits into the casing, which has been taken from the base model, and the equipment clearance, which is user specified. We are designing for the base frequency of 60 Hz, and these pumps are also filtered based on the rate. Now rate here we are going to use intake total rate that is entering into the pump. So each of these pumps has a minimum and maximum recommended flow rate. Also this table has been sorted by keeping the highest efficiency pump at the top. You can also filter this table by selecting pump from a specific manufacturer, for example radar in this case, and I have a bunch of these radar pumps which is suitable for this well. Let me select radar J6200, and based on the size and efficiency, as I have selected this pump, I can see now some of the extra tuning parameters applied here. For example, head derating or power or rate. I can also do viscosity corrections, and for this case it is I'm going to use center lift. Note here that two additional tabs have appeared. The catalog performance curve for the selected pump here. Now if you want to see this plot, you can just hover mouse over one of the data and that gets highlighted, as you can see. Also we have a variable speed curve for the selected pump in case you want to run the pump at different speed. You can see how the pump is going to perform. For more information on any of these, including the tuning factor, you can simply click the help or F1 button, which takes you to the relevant page with description of all the input parameters that we have used. Let's now click at the run button, which is active now after all these data have been completed and the pump is selected. As we run this, once the run is completed, you can see on the left hand side tabulated result as well as bunch of plots appearing on the right hand side. The result tab here has multiple sections including some of the key design input as well as the simulated output across the pump and intake. And as you can see that in this case we need 206 stages, and the total power required for the pump is 493 HP. The right hand side has multiple plots. As you can see, the first of this is a complex well performance with ESP running at multiple speed. It's a complex system analysis. You can also see the actual pump performance curve, which has taken into account all the tuning factors that we have applied here, including viscosity correction. As you can see, coming to the result, we have additional results, that nodal analysis with the ESP in place, and now you can see the well is able to produce we remember we had a design rate of 5,000 barrels per day. Now you can see it's very close here, and this plot is also showing a bubble point line here, which indicates that the pump is operating below bubble point, and that's why we have used gas separator. We also have well pressure and temperature profile. As you can see here, the blue one is the pressure profile and the red one is the temperature profile. You can clearly see the pressure increase across the pump as well as temperature increase. If you are happy with this design, next we can just install this ESP. As we do that, you can see the ESP appears on the wellbore. We can further see the ESP data appearing on the artificial lift tab. This also allows you to change the number of stages to something different if you want, and you can also change the head, flow rate or power factors. Note that all these data, including tuning factors, have been populated from the design task. That concludes my brief demo on ESP design and simulation using Pipesim 2014.